Hello. So, in the last class we have started a tutorial. We have taken up a problem of few feature vectors belonging to class omega 1 and few feature vectors belonging to class omega 2. Actually, the problem that we were trying to solve is the dimensionality reduction problem, that from a higher dimensional space, if I project onto a lower dimensional space, then in many cases the problem that we face, that in higher dimensional space, if the feature vectors belonging to different classes are linearly separable, when I project that into a lower dimensional space, they may not remain linearly separable anymore. And we have also discussed that the best way to project is onto the eigenspace. So, we have taken this particular problem in the previous class, that there are 5 feature vectors which are taken from class omega 1 and there are 5 features which are taken from class omega 2, and we want to find out a projection direction for reduction of the dimensionality that maintains separability between the two classes. That is, even after taking the projection onto a line, the projections of the vectors belonging to class omega 1 and the projection of the vectors belonging to class omega 2, these two set of projected points should still be linearly separable. So, before solving this problem, we have taken up the other issue, that if I project for the best representation of the multidimensional data, and for that we have seen earlier that the best way of projection is to project onto the eigenvector. So, the first problem that we have tried to solve is what will happen to these projected points if the projection is taken on an eigenvector. So, for that, let us briefly recapitulate what we have done. So, this is the entire set of feature vectors, and I want to project these feature vectors onto the eigenvector. So, I have to find out what is the eigenvector. So, for these feature vectors, we have computed the mean vector, and we know that the covariance matrix, the definition of the covariance matrix is sigma is equal to expectation value of x minus mu into x minus mu transpose, where mu is this mean vector. So, for every vector we have computed x minus mu. So, these are x minus mu for different feature vectors, and once I have this x minus mu, for every individual vector x minus mu, we have computed x minus mu into x minus mu transpose, giving me a number of matrices. So, the first one, x 1 minus mu into x minus mu, x 1 minus mu transpose, that gives me a matrix M 1, x 2 minus mu into x 2 minus mu transpose gives me another matrix M 2. Similarly, x 3 minus mu into x 3 minus mu transpose gives me another matrix M 3. Similarly, I get M 4, and as I have total 10 number of feature vectors, so I get 10 such matrices. So, once I have 10 such matrices, I can compute the covariance matrix, which is nothing but expectation value of all these 10 matrices, or effectively these are the average or mean of all these 10 matrices, which gives me the covariance matrix. So, I compute the covariance matrix by taking the mean of all these 10 matrices, and the covariance matrix came out to be this, that is 26.275, 0.35, 0.35 and 2.53. Now, you note an interesting point over here. Always in all the matrices that we have computed, starting from M 1 to M 10, this was a matrix. Yeah, you find that 1 2 and 2 1 is same, 1 2 and 2 1 is same, 1 2 and 2 1 is same, and obviously in the covariance matrix also element 1 2 and element 2 1 is same, because this is the covariance between the first element and the second element x 1 and x 2. So, these two elements have to be same. So, I get the covariance matrix, and to get the eigenvector of this covariance matrix, I have to solve the eigenvalue equation. So, first I have to find out the eigenvalues of this covariance matrix. Out of that, I have to choose the maximum eigenvalue and find out the eigenvector corresponding to the maximum eigenvalue. So, to find out the eigenvalues of the covariance matrix, the equation is, the procedure is well known. You form a determinant of this form. Okay. So, along the main diagonal, if lambda is an eigenvalue, then along the main diagonal from all the elements you subtract lambda, form a determinant and set this determinant value equal to 0. So, I will get a number of equations, solve those equations to find out the value of the lambda. So, that is what I get over here. I get a quadratic equation. You find that it is an equation which is quadratic in terms of lambda, and because it is a quadratic equation, so I will get two values of lambda, or two eigenvalues. So, I get lambda 1 which is 26.28 and I get lambda 2 which is 2.525. So, this matrix, this covariance matrix has two such eigenvalues and out of these two eigenvalues, I have to consider that eigenvalue which is maximum, and corresponding to this eigenvalue, I have to find out the corresponding eigenvector. Okay. So, obviously, if the matrix is of size n by n, I will have n number of eigenvalues. So, it depends upon what is the dimensionality of the matrix, right. So, for this eigenvalue, I try to compute the eigenvector, and for that we have this well known eigenvalue equation, that for matrix A, if x is the eigenvector and lambda is the is the corresponding eigenvalue, then this equation must be satisfied, that is A x is equal to lambda x. In our case, this matrix A is the covariance matrix, which is this, right, 26.275, 0.35, 0.35, 2.53, and this eigenvector x is x 1, x 2, which will be equal to. So, I took the maximum eigenvalue, which is 26.28. So, 26.28 x 1, x 2, I get two simultaneous equations, solve these equations to get the values of x 1 and x 2. So, here you find that x 1 will be equal to 70 and x 2 will be equal to 1. If I try to get the value from the other one, the values will be slightly different, and the values, the difference in values from these two equations, is because of the truncation error. In many cases, the decimal values beyond a certain position we have ignored. So, I get a truncation error. So, because of the truncation error, the x 1, x 2 values that I get from here and the x 1, x 2 value that you get from here, ideally they should be same, but I get a difference because of the truncation error. But anyway, the values will be very close. Instead of 70, here you may get something like 68, 69 or something like that. So, this is my eigenvector. Eigenvector is 71. Then what we have done is, we have plotted all the feature vectors onto a graph paper, okay, and this is the eigenvector 71, projected on all those feature vectors onto the eigenvector, and these are my projected points. And here, as expected, because we did not consider the separability of the feature vectors belonging to two different classes, we just wanted to find out a projection direction that, or a projection space that best represents the higher dimensional feature vectors into a lower dimensional feature vector. So, as we said that it may not be possible to maintain the separability between the classes. And exactly that is what has happened. You find that all the feature vectors, all these feature vectors belonging to class omega 2, they are projected within this space, and all these feature vectors belonging to class omega 1, they are projected within this region, and these two regions now get merged. So, though in the original two dimensional space, the feature vectors belonging to two classes omega 1 and omega 2, they were separable, on the projected space they are no more separable. So, this is a problem that we face if we go for best way of representation or project the original set of data onto the eigenspace for reduction of dimensionality. So, to solve this problem, what Fisher linear discriminator does is, it tries to find out a projection space which maximizes the separability between the classes or separation between different classes, and at the same time it tries to form compact clusters of the feature vectors belonging to individual classes. So, what happens if I have 2 point clouds belonging to 2 different class? When I project it into a lower dimensional space, I try to see that these 2 classes are wide apart, and at the same time the feature vectors belonging to individual class, they are very compact. So, if I can maintain this, I can maintain the separability between the classes even in the projected space or in the lower dimensional space. So, in order to do that, I have to consider 2 things. One is, I have to minimize the within class scatter, so that every class is very compact, and at the same time I have to maximize the between class scatter, that is, the classes should be pushed well apart. So, if I do them simultaneously, then I get a sort of criteria function. So, after optimization of that criteria function, I get a solution vector. So, this solution vector gives me a vector or a projection direction on which if I project higher dimensional feature vectors, even in the lower dimensional projected space, the separability of the vectors can be maintained. Of course, when I tell all about this, my assumption is in the initial space, in the original higher dimensional space, the data points are separated, they are separable. If they are not separable in the original higher dimensional space, then whatever text I play, I cannot guarantee that they will be separable in a lower dimensional projected space. Okay. So, that has to be kept in mind, that when I talk about separability after projecting onto a lower dimensional space, I always assume that in the original higher dimensional space, the feature vectors are well separated. Okay. So, then only the other things are valid. So, by optimization of that criteria function, which minimizes the within class scatter and maximizes the between class scatter, I get a solution which is of this form. That is, if S1 is the within class scatter of the data points belonging to class omega 1, and S2 is the scatter of the data points belonging to class omega 2, then SW, which is equal to S1 plus S2, this is called the total within class scatter. That is, the sum of the scatters of the samples belonging to class omega 1 and the samples belonging to class omega 2. So, I take these 2 scatters individually, then add these 2, I get total within class scatter, which is SW. Mu 1 is the mean of the samples belonging to class omega 1, and mu 2 is the mean of the samples belonging to class omega 2. So, once I have this, then the direction of the projection or the projection vector which maintains separability will be given by S W inverse into mu 1 minus mu 2. So, this solution has been obtained by solving a generalized eigenvalue expression. Okay. So, to illustrate this, I will take up the same problem for which we have gone for projection onto the eigenspace. Okay. So, that is we have two sets of samples, two sets of feature vectors, one set of feature vector belonging to class omega 1, the other set of feature vector belonging to class omega 2. So, the feature vectors which belong to class omega 1 are 1 2, 3 5, 4 3, 5 6 and 7 5. So, these are the 5 feature vectors which are taken from class omega 1. Similarly, 6 2, 9 4, 10 1, 12 3 and 13 6. These are the 5 feature vectors which are taken from class omega 2. Okay. And the scatter of data points belonging to a particular class, they are defined by this. It is the sum of x I minus mu 1 into x I minus mu 1 transpose, where mu 1 is the mean of the feature vectors belonging to class omega 1. So, for every vector belonging to class omega 1, I have to compute every vector x belonging to class omega 1, I have to compute x minus mu or x minus mu 1 into x minus mu 1 transpose. So, when I have n number of feature vectors in belonging to class omega 1, I will have each of these x minus mu 1 into x minus mu 1 transpose gives me matrix. So, if I have n number of feature vectors in class omega 1, I will have n number of such matrices, and sum of all those matrices gives me the scatter of the samples in class omega 1. Similarly, here for every vector belonging to class omega 2, x minus mu 2 into x minus mu 2 transpose, that gives me one matrix, and if there are m number of feature vectors in class omega 2, I will get m such matrices, and sum of all these m matrices gives me the scatter of the samples belonging to class omega 2. So, that is how I compute scatter for class 1 and I compute the scatter for class 2, S 1 and S 2. And you find that there is the scatter and the covariance matrix, they are very, very similar. Okay. If I normalize the scatter matrix by the number of samples that I have, I get a covariance matrix. Okay. Because covariance matrix is nothing but expectation value of this term, which is nothing but take the summation of all these matrices normalized by the number of data elements that I have, the number of matrices that I form, I get a covariance matrix. So, they give more or less same information. In one case it is normalized, in the other case it is not normalized. Okay. So, what I do is I consider these feature vectors belonging to class omega 1 and I compute the mean of all these feature vectors, because finally I have to compute this term. So, I compute the mean of these feature vectors, which is mu 1, and mu 1 in this case will be 4, 4.2, and then considering these feature vectors from class omega 2, the mean of these feature vectors, which is mu 2, is 10, 3.2, which you can easily compute from here. Take the summation of all these components, divide by 5, I get 10. Take the summation of all these second components, divide by 5, you get 3.2, and similarly from here. And the next one I have to compute is for each of the data points, for each of these feature vectors, I have to compute x minus mu 1. For each of the feature vectors over here, I have to compute x minus mu 2. So, that I can compute x minus mu 1 into x 1 minus mu 1 transpose, in the other case x minus mu 2 into x minus mu 2 transpose. So, over here you find that for all the samples belonging to class omega 1, x minus mu 1, when I compute x minus mu 1. Okay. So, x minus mu 1 over here, it will be simply 1 minus 4, that is minus 3 for the first sample, then 2 minus 4.2. So, this will be minus 2.2. Similarly, over here for the second one, it is 3 minus 4, that will be minus 1, 5 minus 4.2, that will be 0.8. Similarly, over here, this will be 0, minus 1.2, here it will be 1, 1.8, and here it will be 3, 0.8. Okay. So, these are x minus mu 1 for individual vectors x. In the same manner, I have to find out x minus mu 2 for individual vectors x belonging to class omega 2. So, let us see what those values will be for the second one. So, here I have to compute x minus mu 2. Okay. So, the first one, it will be 6 minus 10, which is minus 4, 2 minus 3.2, which is minus 1.2. 9 minus 10, which will be minus 1, 4 minus 3.2 is 0.8. 10 minus 10, it will be 0, 1 minus 3.2, it will be minus 2.2. Okay. Similarly, here 12 minus 10 will be 2, 3 minus 3.2 will be minus 0.2, 13 minus 10 it is 3, 6 minus 3.2 it will be 2.8. Okay. So, I have got x minus mu for every individual x belonging to class omega 2. And now, I have to go for computation of the scatter matrices S 1 and S 2. So, for computation of S 1, I have to find out what is x minus mu 1 into x minus mu 1 transpose for every x minus mu 1 taken from class omega 1. So, the first one is minus 3 minus 2.2. So, let us see that what will be this. First one is minus 3 minus 2.2. This is x minus mu 1 into x minus mu 1 transpose will be minus 3 minus 2.2. And if you compute this value, the matrix will be 9, 6.6, 6.6, then 4.84. This is one of the matrices. The second one was minus 1, 0.8. If you remember this, it was minus 1, 0.8. So, it is minus 1, 0.8, the column vector, into minus 1, 0.8 row vector. It will be simply 1 minus 0.8 minus 0.8 and 0.64. For the third one, it was 0, 1.2, 0, 1.2. So, if I compute this, it will be 0, 0, 0, 1.44. For the fourth one, it is 1.8. Okay. So, I will have 1.8 column vector into 1, 1.8 row vector. So, if I multiply this, it will be 1, 1.8, then over here 1.8, and this will be 1.8 into 1.8, that will be 3.24. And then fourth one, x minus mu 1 for the fourth one was 3 and 0.8. So, if I compute this 3, then 0.8, 3, 0.8. If I compute this, it will be 9, 2.4, 2.4 and 0.64. Okay. So, these are the 5 matrices that I have 1, 2, 3, 4, 5. And from these 5 matrices, I have to compute the scatter S1, which is nothing but sum of all these 5 matrices. And if I take the sum, you find that the first component will be 9 plus 1 plus 1 plus 9. So, that is 18 plus 2, which is equal to 20. Similarly, this is 6.4 minus 0.8 plus 1.8 plus 2.4, 6.6 minus 0.8 plus 1.8 plus 2.4. So, this will be simply 10. This term will also be equal to 10, and here I will have 10.8, which is nothing but sum of this plus this plus this plus this plus this, which comes out to be 10.8. So, this is my scatter matrix S1. Similarly, let us try to compute what will be the scatter matrix S2. So, for computation of scatter matrix S2, I have x minus mu 2 over here for every x belonging to class omega 2. So, that is given by this. So, I have to compute the scatter matrix S2. So, the first one is minus 4 minus 1.2. So, the first matrix that I get is minus 4 minus 1.2 into minus 4 minus 1.2. So, that simply becomes 16, 4.8, 4.8 and 1.44. Okay. So, this is what I get from the first vector. The second vector is minus 1, 1.8. So, the matrix that I get from the second vector is minus 1, minus 1, 0.8. Yeah. So, it is minus 1, 0.8 into row vector minus 1, 0.8. So, this matrix will be 1 minus 0.8 minus 0.8, 0.64. For the third one, which is 0 minus 2.2, so it is 0 minus 2.2 into row vector 0 minus 2.2. So, this will simply be 0, 0, 0, then 4.84. So, this is my third matrix. To compute the fourth matrix, it is 2 minus 0.2. So, what I have is 2 minus 0.2 this is the column vector into 2 minus 0.2 the row vector, and if I multiply these two what I get is 4 minus 0.4 minus 0.4 and then 0.04. This is the fourth matrix, and then to get the fifth matrix I have to take this one 3 2.8. So, this is 3 2.8 3 2.8 multiply these two, what I get is 9 8.4 8.4 and then 2.8 into 2.8 it is 7.84. Okay. So, these are the 5 matrices, these are the 5 matrices that I get from the samples, the 5 samples belonging to class omega 2. Now, sum of all these 5 matrices will give me the scatter S 2. So, if you take the sum, scatter S 2 will be given by this. So, I have S 2 which is nothing but sum of all these 5 matrices. So, over here it will be 16 plus 1 17, 17 plus 2 is 21 plus 9 30. So, the first component will be 30, second component 4.8 minus 0.8 minus 0.4 plus 8.4. So, this will be 12, similarly here it will be 12 and this component will be 1.44 plus 0.64 plus 4.84 plus 0.04 plus 7.84. So, this will be simply 14.8. So, you find that I get 2 scatter matrices, one for class omega 1 which is S 1, the other scatter matrix for class omega 2 which is S 2. So, for class omega 1 the scatter matrix S 1 is given by this, and for class omega 2 the scatter matrix S 2 is given by this. Now, from S 1 and S 2 I have to find out what is the total within class scatter, that is S w, which is nothing but S 1 and S 2. So, what I had is I had S 1, I will rewrite here for convenience. I had S 1 which is 20, 10, 10, 10.8 and S 2 which was 30, 12, 12 and then 14.8. So, I have to compute the total within class scatter which is S w, which is nothing but S 1 plus S 2, and this will be simply if I add these two matrices 50, 22, 22 and here 10 plus 8 plus 14 plus 8, that will be 25.6. So, this is my total within class scatter, and from this what I have to compute is S w inverse, because finally the projection direction, because finally I have to compute the projection direction, right, and the projection direction w is given by S w inverse into mu 1 minus mu 2, where mu 1 is the mean of the samples belonging to class omega 1 and mu 2 is the mean of the samples belonging to class omega 2. So, from this total within class scatter SW, I have to compute what is SW inverse. Okay. So, this is what I need to compute. Now, for a two dimensional matrix, 2 by 2 matrix, computation of inverse is very simple. So, if I have a two dimensional matrix something like this, say matrix A, which is given by A, B, C and D, this is a two dimensional matrix, then A inverse is simply given by 1 upon determinant of A, right, and then matrix is D minus B minus C A, which is simply this determinant A is nothing but A D minus B C. So, which is simply 1 upon A D minus B C into D minus B minus C and then A. So, this is what is the inverse of a 2 by 2 matrix, where the 2 by 2 matrix is given by elements A, B, C, D. So, simply by using this expression, when I know that my total within class scatter is W is given by 50, 22, 22, 25.6. This is the total within class scatter. I can very easily compute the inverse of the total within class scatter, that is SW inverse. So, over here this SW inverse will be given by 1 over determinant of SW, that means determinant 50, 22, 22, 25.6, and this matrix will be 25.6 minus 22 minus 22, 20, and this one will be 50. And if you compute this determinant, you find that this determinant is 50 into 25.6 minus 22 into 22, which comes out to be 1 over 796 into 25.6 minus 22 minus 22, 50. And if you complete this computation, the inverse of the matrix will come out to be 0.032 minus 0.03 minus 0.03, 0.06. Okay. So, SW inverse is simply this. So, this is the matrix which is important to me, that is SW inverse. And the other quantity that I have to compute is mu 1 minus mu 2. And we know from before that mu 1 was given by 4.2 and mu 2 was given by 10, 3.2. So, these were the means of the samples belonging to class omega 1 and the mean of the samples belonging to class omega 2. So, I can easily find out that mu 1 minus mu 2 will be is equal to this minus this, that is minus 6, this minus this, which is equal to 1. So, once I have this, the projection direction is simply given by, if I write it as a vector E, is simply S W inverse into mu 1 minus mu 2, that is the direction of projection. Where S W inverse, you remember from the previous sheet, it is 0.032 minus 0.03 minus 0.03, 0.06. Okay. Of course, we are not considering the higher decimal spaces. So, it is 0.032 minus 0.03 minus 0.03, 0.06 into mu 1 minus mu 2, which is nothing but minus 6 1. So, you multiply this by the column vector minus 6 1, and if you compute this, you will find that this one will come out to be minus 0.222 and 0.24. So, the projection direction or the vector on which, if I take the projection which will maintain the separability between the classes, should be this one, okay, which is minus 0.222 and 0.24. So, again let us plot these points on a graph paper and take the projections onto this vector, and let us see what improvement we get at all, if we get some improvement. Okay. So, I will take this graph paper. Right. So, as before, let me assume that, okay, so this is my origin. So, I will draw x axis and y axis over here, or x 1 and x 2 axis. So, this is x 1 axis and this is x 2 axis. Okay. Let us put the vectors belonging to class omega 1, and I will use this green color for that. The vectors are 1 2, then 3 5. If you remember these vectors which we had used, 1 2 3 5 4 3 5 6 and 7 5 from class omega 1, 6 2 9 4 10 1 12 3 and 13 6 from class omega 2. So, for class omega 1 it is 1 2, the next one is 3 5, next one is 4 3, that is over here, the next one is 5 1 2 3 4 5, 1 2 3 4 5 6, 5 6, which is over here. The next one is 7 5, 1 2 3 4 5 6 7, 1 2 3 4 5 7 5. So, these are the vectors which are taken from class omega 1. Similarly, if I take the vectors from class omega 2, which are 6 2, 6 2, 9 4, 10 1, 12 3 and 13 6. So, I will take 6 2 1, 2, 3, 4, 5, 6, 6, 2 is over here. Then 9, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 2, 3, 4, this is 9, 4, then comes 10, 1, 10, 1, then comes 12, 3, 12, 1, 2, 3, and then 13, 6, 13, 1, 2, 3, 4, 5, 6, 13, 6. So, these are the vectors from class omega 2, and my projection direction as we have computed is minus 0.222 and 0.24. Okay. So, I will put it as, let us truncate this point, say minus 0.22 minus 0.24, minus 0.22 and plus 0.24. So, I will multiply, because I am interested only in the direction. So, even if I multiply this by 10 does not matter. So, I will take it as minus 2.2 multiplying this by 10, minus 2.2 and 2.4. So, I will take this point minus 2 or even minus 22. If I multiply this by 100, even that does not matter. So, I will make it minus 22 and then plus 24. So, minus 22 is somewhere over here, plus 24 is over here. Okay. So, this is the point. So, my vector is this is the direction of projection, right. Now, let us project or take the perpendicular projection of all the feature vectors belonging to class omega 1 and the feature vectors belonging to class omega 2 onto this projection direction. So, which will be, if I take the perpendicular projection, okay. So, these are the projections, right. So, now we find that when I projected the feature vectors belonging to class omega 1 onto this projection vector and the feature vectors belonging to class omega 2 onto the projection vector, they are not mixed anymore, they are well separated. So, over here this is the region in which the feature vectors belonging to class omega 1 they get projected, and this is the region over which the feature vectors belonging to class omega 2 they are projected, and these two regions are well separated. So, the projected points are no more mixed, unlike in the previous case. If you remember this particular figure, where the feature vectors from two different classes they are mixed in this region. Okay. So, the projected points are no more separable. But if I maintain that constant, that when I try to take the projection directions, I will maintain the separability. I will try to maximize the separability between the classes, or I will try to maximize the between class scatter, and I will try to minimize the within class scatter. So, while doing so, the solution vector or the projection direction that I get is this, and here it is quite clear. This demonstrates that on this direction, if I take the projections, even in the projected space, the feature vectors in different classes, they are well separated. Okay. So, this solves one part of the problem, that is, I have been able to reduce the dimensionality. But for classification application, I need to go further, that is, I have to design a classifier which works in this projected space. Okay. So, how do I do that? Clearly, over here, these are one dimensional variables, all these projected points. If I take the distance of these points from the center, these are one dimensional variables. So, I get a set of one dimensional values or scalar values over here. I also get a set of scalar values over here. So, I take this set of scalar values to belong to one class, and this set of scalar values belonging to another, that belong to another class. And for classification purpose, what I need to do is, I need to identify a point on this line which will separate between these two classes. Okay. So, if these points follow a particular distribution, I can find out what is the mean and variance of this set of points. I can also find out what is the mean and variance of this set of points, and from there I can identify what should be the threshold on this line. Okay. So, this is not a big problem, but it is a very simple problem. So, through this what we have done is, we have reduced the problem from a higher dimensional space to a lower dimensional space, and the lower dimensional space, the problem is more manageable. So, I stop this lecture here. Thank you.